Okay, so my name is Lukas Krejci, as you heard just a few seconds ago, and I'm going to talk about relation between test coverage and timed automata model structure. So first I will tell you something about the background of our research and the model description, the case study that we are using, of course the experiments and the results and conclusions. So basically what we are doing is integration testing of automotive systems. Integration testing is basically evaluation of the system as a whole. So the individual components are interconnected together, and basically the functions of the systems are distributed among multiple control units. All those control units have been obviously unit tested, but there might be still some bugs due to misinterpretation of specification or due to communication errors. And this is what integration testing is for, and it's a very important part of testing of automotive system, because in a recent era the number of control units in automotive systems are rising, and it's getting more serious as we are on the beginning of the era of autonomous vehicles. Basically, nowadays the integration testing is done independently by each car manufacturer, and the problem is that the control units can be manufactured by different company. So, for example, we are cooperating with Škoda Auto, that's a company which is part of Volkswagen Group, and they get control units from Volkswagen, from Audi, their own control units. So it's kind of like a big mess of control units, and each of this company is doing their separate unit tests, but basically it still needs to be tested as a whole. This is usually done using the hardware in the loop principle. So the real hardware, the real control units are interconnected on a test bed, and this test bed is driven by simulation mainframe that is providing input stimuli to the system. And the problem is that those integration tests are currently designed manually. Automotive corporations are very strict about, let's say, non-disclosure agreements, and they like to keep secrets, so they obviously don't want the competitors to know how their system works, so everything is closed. They have their own tests, nothing is basically automated. There are basically test cases stored in the testing backend, and that can be problematic as the complexity of the automotive system grows, which is happening nowadays because of the autonomous vehicles and multiple driving assistants that you have in cars. And therefore it's suitable to automate those tests, and our team is trying to propose methods and tools and develop tools for model-based testing or for application of model-based testing principles for automatic generation of those tests for automotive systems. So this is basically the workflow that we are currently working with now. So we have some specification of the system that corresponds to the system under test, which is the entire car or part of the car. And from this specification we need to create model, and this model is loaded into our tool that is called Taster. That's the model-based testing tool that we are using or that we develop. And this Taster tool is interacting with Exam, which is test management software developed by Audi and currently managed by or maintained by Micronova. And the Exam is interacting with the test bed and its testing backend, which provides some level of abstraction from like the simulation mainframe, because there can be multiple technologies for and multiple suppliers of the simulation mainframes like Micronova, DSpace, or National Instruments. So our team actually developed a testing platform for hardware-in-the-loop testing of automotive systems. So what you can see here is test bed with real control units, real car parts. You can see there are some car lights. We have simulation of the window sliders. We have simulation of windscreen wipers. And we also have simulation of automatic trunk doors and simulation of power steering. And some more complex test beds even contain simulation of engines and propulsion, or electrical drive if it's electrical car. So the case study we were working on, or we are working on, is focused on the automatic trunk doors control system and the keyless locking system. So basically, we used as a modeling language, we used timed automata, which is extension of Finnish state machines. It was introduced in 50s by Clark and Dale, and it was enriched by multiple extensions over the time. To be exact, we are working with extension introduced by team who developed the UPAL model checker, which is maintained by team on Upala University. And they basically extended the timed automata systems by variables and synchronization capabilities. So the time automata can be organized into networks that are synchronized. And so our system under test, as I said, is composed from two parts. First part is the trunk door control unit. So as you know, many modern cars have the automatic trunk doors, so you can set like the level to which the trunk doors should be open. There is a button for closing the trunk door. You have the virtual pedal mechanism, so you just put your feet under the bumper and the trunk opens. And the second part for the case study is the keyless locking system. So basically, that's the system that allows you to approach your car with your keys in your pocket, and once you touch the handle, the car automatically unlocks. But what is the problem that we have here? Basically, it's the lack of guidelines how to model such systems, because automotive systems are reactive, are real-time, and are distributed. And of course, the timed automata networks allow us to model such systems quite easily, but there is no guideline how exactly those models should look like. So in model-based testing, you need observer part and environment part. Environment represents the environment of the system under test, which is user. It can be like atmospheric conditions or like the situation on the road and such. And the observer represents the correct behavior of this tested system. And basically both of those parts can be modeled differently. For example, you can have fully permissive approach, which effectively generates random stimuli to the system, and the system under test is modeled like in details, and that's kind of useful for uncovering corner cases. But it also produces a large number of like non-sensual tests, so or unrealistic scenarios. So there is a second approach, which is called fully restrictive, which basically reduces the possible traces in the system. For example, the user is, or the car user or the driver is modeled more realistically. And the question that we were trying to answer is which of those approaches is like best from the point of view of coverage of the observer model. That's fairly important, because while the coverage isn't like ideal for like a primary guidance for testing, it's very useful for augmenting the existing strategies. So therefore we created multiple variants for environment and multiple variants for observer parts. So for example, this is a very simple example of a simple environment model, or one automaton from the environment model. This represents one button, basically. So each button is represented by one individual automaton like this. And this can be, for example, the button on the trunk doors, the button inside the trunk, the button on the driver dashboard, on the keys. And each of those buttons is represented by one automaton like this. There is also one automaton that changes the positions of the keys or the key transmitter with respect to the car. Those models are very easy to create, so that's big advantage. This is an example of complex environment model, which is basically modeled after realistic behavior of a driver. So driver first comes to the car, unlocks the car, then manipulates with the trunk, opens it, closes it, and locks the car and walks away. And this generates more realistic test cases, but it doesn't have to necessarily uncover all the corner cases that are possible within system. Simple observer model basically is in principle very similar to the simple environment model. So each individual subsystem in the system under test is modeled but separate automaton. And so this is the example of the model of trunk doors control, and this is an example of model for the keyless locking system. And the complex environment, complex observer model basically models the full system, the entire system as a whole from the user point of view or from the specification point of view, which basically represents like more restrictive description of the system under test, but at the same time it might provide some more realistic test cases, or represents the more realistic behavior of the tested system. So basically we were comparing all those model variants with respect to the coverage criteria or structure model coverage criteria, to be exact, because in the automotive systems we have to work with black box testing. We can't have access to the control units, source codes or anything, so we just get like control units that are plugged into the test bed, and that's all we have. So we picked three criteria. We picked node coverage criteria, edge coverage criteria, and edge pairs coverage criteria. And we tried three different strategies. Random is basically just a stochastic walk in the state space. Systematic always picks the transition that has least take count. And heuristic strategy takes into account hints encoded on the edges of the model. So we were using the taster tool, as I said before. So this is a screenshot of the tool, and behind it is the exam environment, or the test management environment. So the results. So these are the results for node coverage. So as you can see, the simple combination of simple observer and simple environment, which means everything was modeled as separate automaton, has provided the most stable results, except the part with heuristic strategy, where the complex environment seem to perform slightly better, which makes sense because only the environmental model or the complex environmental model contained those hints that were used by the heuristic strategy. In terms of edge coverage, again, the simple variant or the simple variant provides very stable results. We can see that systematic strategy is somehow underperforming, especially in the case of complex environment, which means the realistic driver. And the edge pairs coverage, which is important. Okay, I should also mention why are those criteria important. So node coverage is important because the invariants of the tested systems are encoded on nodes. Edge coverage has basically encoded information about executed actions with the system under test, and edge pairs coverage is basically just extension because sometimes the bugs are triggered by specific sequences in the tested system. So in the edge pair coverage, we can see that again, simple variant provided very stable results, but there is somehow surprisingly underperforming variant of the simple observer and complex environment, which is expected, however, because obviously when we have like a detailed model of tested system and we have restrictive environment, it can't possibly test all the possibilities that can happen within the system. So in conclusions, the most promising combinations seem the simple environment and simple observer, which means the approach where everything is modeled as separate automaton. Obviously, the worst performance of the complex environment is expected, as I said, but that doesn't mean that this model shouldn't be used. And the complex observer model was providing good results in some cases, however, they weren't very stable. So that's actually suggests a very optimistic outcome that is more beneficial to create simpler models that are easier to make, which is basically what we want. And future work will basically consist of two parts. First part is extension of the case study. So we want to add, for example, propulsion system model, intrusion detection model, and other systems. So like light control system, windscreen controls, and others. And of course, we need to evaluate the other testing strategies or multiple testing strategies. For example, currently we are working on a strategy that is utilizing the machine learning. So thank you for your attention, and if you have any questions.